So once again, good afternoon to those who just joined, and welcome to KIT 458 Chemical Processing Lecture. We are going to resume what we have learned yesterday. Okay. Before that, maybe I can share the slides with you guys. So I guess yesterday we have gone through on partial oxidation. Okay. We've gone through partial oxidation process, and then we also have looked on other things. For example, on the process, okay, as well as the other methods like cold gasification process. Comparison, this is the homework that I need you guys to do. I have created the event on your e-learning, so please find some time and then do the homework. I've set the deadline till Friday. So at least you can have enough time to read through a few techniques which I have listed over here and discuss the advantages and disadvantages. We also gone through on oxygen, production of oxygen. Okay. And regarding on the higher oxygen purity process. For today, actually, we are going to finish off chapter 2. The last part of chapter 2 is basically on liquefaction or gas refrigeration. I think all the while we have looked into some process which compress the gas and then convert it into liquid gas. And I believe it is important for you guys to understand the principle of liquefaction. Okay. But probably for that, I just approve a few students who wanted to join. Right. Okay. So liquefaction of gas is basically a conversion of state, okay, from gas into liquid. So this actually proceeds via condensation process. That is actually the definition of liquefaction. Meanwhile, the detailed definition of liquefaction is actually the refinery process of converting natural gas or other gases hydrocarbon into longer chain hydrocarbon such as gasoline or diesel fuel. So this where liquefaction applies. Sometimes in oil and gas, you will have natural gas as a source, and then liquefaction will be one of the best method that separates gases hydrocarbon, and then with the other types of long chain, like other types of hydrocarbons chemicals. So the picture that you see over here is basically a very old process, how the scientists those days produce liquid gas. This actually function as a compressor. So the person will actually turn this rotor, and then what happens is it will build up a pressure. It goes into this chamber, and then after that of the pressure, what happens is the liquid gas can be formed when you cool it. Okay, so that is why sometimes when you see over here refrigeration, it means that the gas being cooled and then it will change the state into liquid state. The either gas refrigeration, by principle, it is actually by moving heat from a cool reservoir, okay, to a warm reservoir, which normally requires energy. The amount of heat removed is associated with the amount of entropy by the relation of dQ. Okay, Q is actually heat that is equal to temperature with a difference of entropy. Okay, an ideal process, the entropy associated with the two heat flows is the same. So that is why you'll see that ds is actually equals to dq over dt, okay, or t, which in this case c, yeah, c is actually known as critical, and h is actually heat. An ideal process, the amount of work required to move the heat is equal as follows. The difference of work equals to difference of heat, I mean H minus with dqc. Methods for gas liquefaction, there's several methods. Okay, this actually to attain cryogenic temperatures. How you can maintain the cryogenic temperature. As I mentioned to you earlier, anything that deals with the term cryogenic, it means that this related with cooling process. So several methods actually need to be considered. Okay, the gas need to be compressed at the temperature less than its critical temperature. This will make sure that the gas will do work against the external force, causing the gas to lose energy and change to a liquid state. And then the gas will work against its own internal force, causing it to lose energy and later on liquefy. There are several methods that you need to remember. Okay? This is actually important. You have Joule-Thomson effect, which actually explains that it compress and then after that rapidly expand the gas. So one of the examples of Joule-Thomson effect is Lin-Hampson cycle. We are going to go to this effect one by one. The other one is actually known as cloud effect. In the cloud effect, actually it uses the expansion of engine. Okay, not the same as Joule-Thomson, where in cloud it's more or less the gas. I mean the gas being expand using engine, using mechanically engine. Some methods that is famous is Kapitsa cycle and also Helen cycle. Joule-Thomson effect. In 1885, Joule and Thomson confirmed that a gas flow through a restriction experience a temperature drop along with the pressure drop. So the Joule-Thomson coefficient is equals as follows. Mu J is actually known as the mobility of gas, mu, equals to the change of temperature over the change of pressure. This actually will characterize the phenomenon when you have mu J is greater than 0. This tells you that the cooling will accompany a pressure drop. The region of positive and negative mu J are reflected with temperature to entropy diagram and inversion curve. So later on you will see over here, okay, that the temperature have some effect in terms of the entropy values as well. I mean, for example, if you increase the temperature, the entropy values are going to be changed as well, right? So this is actually an example of a different gas. Above the inversion temperature, we have mu J that is less or equal to 0 for all pressure. The pre-cooling is required for helium, which have the critical temperature around 45 Kelvin, hydrogen 205 Kelvin, and then neon at around 250. So this actually tells you that the pre-cooling is required for the gas to achieve critical temperature. And once it reaches critical temperature, then the gas will be converted into liquid. So this is one of the example of Joule-Thomson effect known as simple Lin-Hampson cycle. Right. This cycle is considered important. I hope you guys can have some time to digest it. Right. So for Lin-Hampson cycle, you'll see that over here, this is actually where the markup gas will be inserted. Okay? It will insert it into a piston or a compressor. Then some amount of force or work will be applied to this compressor. So the resultant heat will be equals to QR, okay, the relative heat. And then after it has been compressed, it goes into the heat exchanger. So this heat exchanger actually functions to cool the compressed gas, and then what happened? Condensation process occurs, and later on it goes into the Joule-Thomson valve. So the liquid will be collected and kept in the liquid reservoir. So this liquid reservoir, the atmospheric condition is considered vacuum. Okay, so you don't have any atmospheric air that can penetrate to this vessel, and then it's still like maintained in liquid reservoir. What will happen if there's a sudden increase in temperature in this liquid reservoir? Then the liquid will be converted into gas. Okay, so when it converted into gas, it will actually use again for the production of liquid gas again. So this is basically the principle. So over here, you will notice that there's 1, 2, 3, 4, 5. There's a 5 steps that actually explain what you will experience. So over here, this is actually the temperature to entropy profile. You can see over here that at the high temperature, okay, with a high value of entropy, what happened is actually you decrease, okay, the entropy. How the entropy decrease? Because you apply some work over here. You compress it. So this actually tells you that when you compress, okay, when you compress the material, it will actually decrease the entropy. So the entropy values will be reduced, okay, and then after that, this is where cooling process start to occur. So you'll see that the temperature start to decrease, okay, until it reach 0.3. So 0.3 is where the critical temperature achieved, and the gas will be converted into gas. Sorry, the gas will be converted into liquid. So this is where the region, the gas established as a liquid gas, okay, and if, like for example, there's sudden increase, this G, the sudden increase in terms of temperature, or maybe sudden expansion due to exposure, then the entropy will increase, and then if there's anything related with increase of temperature, it goes up again, and then same thing, it become gas, and the cycle is like that. So this is actually known as a simple Lin-Hampson cycle. The principle is very basic because it uses only one compressor, one heat exchanger, which is a cooler, okay, and then after it reached the critical temperature of gas, it will convert it into liquid. So the inversion temperature must be above compression temperature or pre-cooling via a higher temperature refrigerant liquid that is required. Recuperative heat exchanger pre-cools the high pressure streams, and this will actually will require liquefier, okay, as a source of markup gas. And finally, the refrigerator will absorb the heat, converting the liquid to vapor at saturation temperature of a lower pressure. Any questions so far for simple Lin-Hampson cycle? Anything? Anything that you want to ask? Moving on to the next one. This is basically a simple Lin-Hampson cycle enhancement. What does it mean by enhancement? Enhancement means that the process has been probably improvised in terms of the properties, the process, and whatsoever. Here you will see that there's two versions of Enhancement cycle. There's one that is known as pre-cool Enhancement cycle, and another one is actually known as dual pressure Enhancement cycle. For this two cycle, actually it used two compressor. You'll see for the pre-cool Enhancement cycle, this is where the start is. The first gas will goes into the piston or the compressor, and the work will be applied. So still the same thing happens. Okay, the entropy will be decreased, and then it goes to the heat exchanger. So heat exchanger function to cool the gas. Okay, in fact, two cooler is installed here. So this actually to ensure that the gas will be like definitely liquefied. Okay, and after that it will be kept in the reservoir, liquid reservoir. So some you will notice that the gas will goes to another source of refrigerant condenser. Okay? And some actually goes into the second compression. So this is in the case of when you have a certain gas that is evaporated. So the gas that has been evaporated goes back into the second compressor, and then will be chill, and then it goes back to the stream so that you wouldn't lose anything. So the pre-cool Enhancement cycle actually optimize the performance via pressure, pre-cooling temperature, and mass flow ratio. Okay, so the factor of material is increased by the factor of 2, right? And for the dual pressure Enhancement cycle, this actually have a different principle, because over here the markup gas will goes into the first compressor. Next, it will goes into the second compressor. So the difference between these two compressors is that the first compressor actually applies at the lower pressure. So the amount of work or load over here applied is not as high as the second compressor. So the first one actually applies at the lower pressure, and then it can immediately goes into the next compressor, which applies at the high pressure, and then goes into a chiller. Chiller will liquefy the gas, and then the gas will be the liquid gas will be kept in the reservoir. So you'll see even here there's like several or a few channels of heat exchanger for cooler. This is actually to ensure that the gas didn't evaporate. Okay, and in fact, if it is evaporate, it will goes back, it will recycle back to the compressor one. Okay, and once after it kept in the liquid reservoir, it can be stored and kept for several years or for the next purpose. Right. So for dual pressure Enhancement cycle, optimize the performance with two pressure and the fractional mass flow. And then the factor of materials is increased as a factor of 1.9. So it's the factor of material is almost the same, not much different. And next, we are moving on to the cloud cycle. So for cloud cycle, this is actually related with isentropic expansion. Anyone knows what does it mean by isentropic? Anyone wanted to try or understand what does it mean by isentropic? Anyone? Maybe got names. Chong Shu Chong Shu Ang? Chong Shu Ang?
Yes, doctor.
Yeah. So what does it mean by isentropic? Any idea?
No.
Okay. I believe you've learned about gas in KFT, right? So not sure whether you guys still remember what does it mean by isentropic. Okay. So isentropic is basically defined as a process of idealized thermodynamic process and it is actually adiabatic and reversible. So when I said adiabatic, what does it mean by adiabatic? Adiabatic, have you heard about adiabatic? Process before?
Yes, doctor.
Yeah. So what does it mean by adiabatic?
No change in heat. Q is equal to 0.
Okay. So adiabatic actually means that the thermodynamic process occurs without any transfer of heat or mass. So as you said, maybe heat of mass is equal to 0 lah. Without transferring of heat, the process of thermodynamic. Okay. So this is actually the direct definition of adiabatic process. Okay, right. So basically, for isentropic expansion, it can be categorized by mu s, okay, equals to dt over dp, right? Where the value is always greater than 0 as a result in larger temperature drop for a given pressure than with isenthalpic expansion. So the first and second law analysis will give this representation. I believe this one is not really something that you have to memorize or whatsoever. It's just a fundamental concept for you guys to understand the first and second law principles of isentropic expansion. So over here, you will see that in the cloud cycle, okay, it actually installed as much as heat exchanger. Okay. Earlier on, for simple Lin-Hampson, you will see only one. In fact, for the two types of Lin-Hampson cycle enhancement, basically is like one. But when you have a possibility that it undergo pre-cool, then of course you will have two. But I think for a dual pressure, normally you will only have one times cooling. For isentropic expansion from cloud cycle, you will see that over here, the first markup gas will go into the compressor. Okay, a load will be applied, and then you will see that the entropy will be decreased. Okay, so once you increase the pressure, okay, the entropy value will be decreased. Then it goes to the first cooler, first heat exchanger. Okay, so you'll see that the temperature will slightly drop, okay, 2 to 3, and then further it will be cool in the next heat exchanger from 3 to 4, and then followed by the third heat exchanger, 4 to 5. Okay, and finally it reached the critical temperature and converted or liquefied. Then it will be kept in the liquid reservoir. Things that you need to notice over here is that there's an installment or there's an installation of expander. Okay, so the expander actually works during the recycle of the gas. So when there's an increase of entropy, probably in the reservoir tank, okay, the pressure will be decreased. So what will happen is you will see there's an increment of entropy. Okay, and then after that, when it is recycled back, it goes to the expander because most of the gas over here is compressed, so it will be expand back and goes back into the markup gas. All right. So the temperature to entropy profile is more or less the same as Lin-Hampson, but instead over here you will see that for the cooling process you have several steps, 1, 2, 3, because of you have 3 heat exchanger. In fact, after the temperature have increased, it need to go to the 3 heat exchanger also. So you have like 1, 2, 3, okay, and finally back to 1 again. So this is actually the cycle. Cloud cycle also have several variation, still performing using at least two heat exchanger, and expander is still installed during the recycle process. Okay, so you have like two variation. You have Kapitsa cycle. Kapitsa cycle actually applies the compression at a low pressure. Okay, normally at around 7 atm with a regenerative heat exchanger. Meanwhile, for Helen cycle, it applies at a higher pressure, okay, 200 atm and liquefaction. And for the expander, it uses a room temperature expander. So Bahar principles is almost the same, except that for Kapitza is the amount of load applied for compression is low pressure. Meanwhile, for Helen is normally at higher pressure. Okay. So I hope you guys can understand or can memorize a bit on the cloud cycle and the simple Enhancement cycle. Right. So the last part of this chapter related on liquefaction is on the separation. So after you know how to produce liquid gas, you have to understand that liquefaction is also used for the separation of different gas. Because by principle, every chemical has its own flash point or probably boiling temperature. So this actually will be a useful tool or indication how you can separate the material. Imagine that if you have natural gas is a combination of a lot of gas. Then if you know specifically where does this gas evaporate or boil, then of course you can use it as a guideline for the separation. So liquid natural gas, LNG, okay, this you'll see a lot in cooking gas, and some vehicle also use LNG. Okay, liquid natural gas is liquefied at the temperature of minus 160 degrees C. Okay. The volume will be reduced as much as 600 times. Imagine from the volume of the gas 600, and then after that, when it is compressed and liquefied, it has been reduced in terms of the volume to 600 times. Liquid natural gas, colorless and odorless, and is also known as non-toxic. It is safe to transport and store, and normally shipped and stored at the atmospheric pressure. So this is where the liquid natural gas can be produced. First, the natural gas will be excavated from or extracted from oil well or probably from the oil rig. Then what happens next is it goes into the field processing. It goes into the transmission pipeline for process. And then this is where liquefaction performed. It will be compressed and cooled. Then after that, the liquid natural gas can be later shipped and used to the end user. More or less, this is actually the process flow. You see, the natural gas will be goes into the treatment and purification. So sometimes treatment and purification is important to remove some condensates, like some hydrocarbons, okay, CO2, mercury, and hydrogen sulfide, H2S. It also will cause dehydration because most of the water will be removed here. Okay, and next the gas will goes into the coolant. Okay, into the cooler. So what happened is, yeah, before it goes into the cooler, it will be compressed. Okay, compressed, goes into the cooler. It forms a liquid natural gas, and then after that, the liquid natural gas will be stored. Okay, so there's a link for YouTube. I believe later on we will watch it. This. Okay. So the advantages of gas separation via liquefaction process. Of course, for this type of process, it will not include heating. So there's virtually no ash, no sludge, or no hazardous waste produced, no other gas, hazardous gas produced. The particulate emission are approximately 95% less than burning charcoal. Okay, so over charcoal, distillate, and naphtha, LNG has a lower sulfur dioxide emission. Okay, around 100% because no sulfur dioxide produced during the production of LNG. For nitrogen oxide, the emission been reduced like by 75, only 25% of nitrogen oxide produced and around 50% of carbon dioxide emission reduced. Okay, so I guess I will share with you guys a few videos related on the conversion of natural gas into liquid natural gas. Is there any questions so far? I think while waiting for the videos to load, just ask. Any questions so far? Anything? Okay. You can guess. Wait, huh?
The world's population is growing, and for many, living standards will continue to improve. As a result, global energy demand is in 2050 when compared to 2000.
But before that, can you guys hear the voice? I don't know. Can you guys hear the voice?
Yes, doctor.
No. Ah, okay. You can hear the voice.
To help gas an increasingly important role. Natural gas is plentiful and is the cleanest burning fossil fuel. But some natural gas resources are in remote locations. Transporting the gas long distances by pipeline can be costly and impractical. The solution? We liquefy the gas by cooling it, which shrinks its volume for easier, economical, safe transportation by ship. So how is liquefied natural gas juiced? Natural gas extracted from the ground contains impurities, water, and other associated liquids. First, it is processed to clean it. It goes through a series of pipes and vessels where gravity helps separate the gas from some of the heavier liquids. Other impurities are then stripped out. The natural gas passes through a water-based solvent that absorbs carbon dioxide and hydrogen sulfide. These would otherwise freeze when the gas is cooled and so cause blockages. Next, the remaining water is removed, as this would also freeze. Finally, remaining lighter natural gas liquids, mainly propane and butane, are extracted to be sold separately or used as a refrigerant later in the cooling process. Traces of mercury are also filtered out. Now the purified natural gas, methane, some ethane, is ready to be liquefied. This happens in heat exchangers. The cooler, chilled by giant refrigerators, absorbs the heat from the natural gas. It cools the gas to minus 162 degrees centigrade, shrinking its volume by 600 times. This turns it into a clear, colorless, non-toxic liquid, liquefied natural gas, or LNG, that is much easier to store and transport. The LNG is kept in insulated tanks, until it is ready for loading into a specially designed LNG ship or carrier. When the ship arrives at its destination, the LNG is transferred to a regasification plant where it is heated, returning it to its gaseous state. The gas is then transported via pipelines to customers, providing energy for homes and industry. Shell continues to help meet growing energy demand with cleaner burning natural gas.
Okay, right. So, okay. There's also another video. Show you guys.
Grammarly catch air. With Grammarly, you can find really good. Perfect if you're writing sharp or explicit or excellent.
Welcome to today's lectures. So today we'll talk about the liquefaction of gases and the critical phenomena. So what is liquefaction of gases and critical phenomena?
I think this one is, the concept of liquefaction of gas. Maybe this one is more of like a lecture. So, yeah, maybe this one is not needed. Okay, all right. So, any questions so far regarding on liquefaction? Anything that you want to ask? You still can hear my voice? Hopefully, yes. Yeah. Can someone give a response? Can you guys hear my voice? Oh,
Can, Doctor.
oh yeah. Okay. That's good. So without further ado, I will start the next chapter. The next chapter is actually on salts and alkali. Share the slides first with you guys. Okay, right. But probably today I'm not going to go to this detail. Maybe just slight introduction about this chapter. Okay, and perhaps we'll continue it on the next day. Chapter 3 is basically on salts and chlor-alkali industries. In this chapter, actually, you will learn how you are going to produce different types of salts, normally like soda ash, caustic soda, okay? And the source of this salt is actually coming from brine solution. So brine actually seawater, for those who didn't know what does it mean by brine, okay? So several other things which normally produce during the production of soda ash or caustic soda is normally the gas. So that is why it is also known as chlor-alkali, because it also produces other types of salts, caustic soda. At the same time, it also produces other types of gas like chlorine gas. Okay, so things that you are going to address in this chapter is, of course, what would be the source, okay, to produce this kind of salts, what would be the types, how you can purify, and how you can use NaCl solution, okay, and then you will learn about the electrolysis of brine, because I think for the production of the salts and chloralkali chemicals, you will have like 3 different cell, electrolysis cell that you are going to learn. And then what will be the economy and the uses of the products, right? So the chloralkali industries, you've seen it a lot. Normally the types of chemicals that is related with this industry is caustic soda, okay, soda ash, and also chlorine. So caustic soda means that you produce NaOH. So why it is named as caustic? Because it has a slightly basic properties. That is why it is known as caustic soda. Soda ash is basically sodium carbonate. Okay, you will see it a lot for the production of glass and whatsoever. And chlorine gas is normally used for bleaching. Okay, the appearance will be yellow in color. And chloralkali industries actually have a rank close to sulfuric acids and ammonia in the magnitude of dollar values of use. So meaning that the high demands of chloralkali industries due to several chemical process uses it as the raw material. A lot of consumption in making other chemicals. This what I've said just now, because normally caustic soda, soda ash, and chlorine is used for various types of chemical synthesis and whatnot. The uses can be various. It can be used in the soap production, detergents, fiber and plastic, glass, petrochemicals, pulp and paper, fertilizer, explosive, solvents, and other types of chemicals. So basically, you will see over here that in the chloralkali industries, the types of chemical produced, like for example, chlorine, normally used for paper and pulp process. Okay. Solvents also use chlorine, plastics, pesticide, and whatsoever. For caustic soda, normally for the production of soap, rayon, okay, dyes, paper, drugs, and other things. Meanwhile, for soda ash, sodium carbonate, apart from soap, glass, it is also used in ceramic, textile, metallurgy, chemical, sugar, foods, and others. Okay? And finally, you also have sodium bicarbonate, which normally produced during the production of soda ash. Okay? Bicarbonate, you've heard it a lot for the production of baking powder, food products, fire extinguisher, beverages, and others. Okay, so I believe probably you have used sodium hydroxide or caustic soda in your final year projects and other types of chemical synthesis. So caustic soda previously made by causticization of soda ash with lime. Okay, so lime is actually calcite or calcium hydroxide. So you see that soda ash, which is sodium carbonate, reacted with calcium hydroxide, produce soda ash, caustic soda, NaOH, plus with calcium carbonate. Okay. Only 10% of sodium hydroxide produced or obtained from causticization process. So that is why there's a need of other techniques which actually produce more percent yield. In this case, the electrolysis of brine will be used. It is the most popular method adopted nowadays. Caustic soda appearance normally brittle white solids, and it has actually a hygroscopic features. Hygroscopic, it means that it can absorb moisture or water easily. So imagine that if you open or you take out a few sodium hydroxide pellets and you put it outside, what you can see, it become wet. It become like a lot of water or what absorbing it. Okay, it's not meaning that it's melted, but actually it absorbs water, because as I said, it is hygroscopic. And at the same time, when water has been absorbed, it will dissolve the material, and then you will see that it become liquid. It's sold on the basis of sodium oxide content, where 76% of sodium oxide equivalent will produce around 98% of sodium hydroxide. And the application, of course, it is used for the soap, textile, chemicals, and petroleum refinery. So, of course, the application, the uses of caustic soda might varies, mostly for chemical manufacturing around 50%, pulp and paper 20%, cleaning 6%, and others. Okay, right. So I believe for the manufacturing of caustic soda, this will be continued in the next lecture. Okay, and I guess tomorrow, for your information, we are not going to have lecture. Suppose we have a lecture tomorrow, but we already replaced it with class yesterday. And then for Thursday, okay, for Thursday, I'm going to do the lecture in the evening, meaning that we are going to have maybe around 1 hour lecture from 8 to before 9, just to replace the class in the early morning, because I have a, as I said, I have a workshop tomorrow and day after tomorrow. So the class for Thursday will be replaced in the evening, and then tomorrow you will have no class. And forgot to tell you that later tomorrow morning, okay, I will post your quiz, the first quiz, okay, which related on chapter 1, okay. So you guys can do it, and probably I will give I think a deadline or submission before 5 p.m. So this can be downloaded from your e-learning, and then you can try to do and then post it in the form of PDF still at your e-learning portal, right? So before I call for the day of today's lecture, is there any questions so far? Anything that you want to ask regarding on liquefaction or other things? Probably this one we have not gone to too detailed, it's just the intro part. Any questions so far? Anything? Right. So if there's no question, then I will adjourn the class. Please again fill in your attendance from the Google form, and those who have watched or already attended the lecture yesterday, I mean last night, please, submit your attendance as well. Okay. So need not to worry. Today's lecture is also recorded, and if you have any doubts, you can watch again the video, and you are free to ask in the next class or during the discussion. So with that, thank you very much for your kind attention. I'll see you Thursday evening. Thank you very much. Assalamualaikum, and see you guys Thursday.
Thank you, Doctor.
Okay.